Hey, hi everyone. My name is Martín Costa, and today I'm going to be talking about our recent stock paper, Vizing's theorem in near linear time. This is joint work with Assadi, Sohail Behnezhad, Sham Bhattacharya, Shai Solomon, and Tianyi Zhang. Okay, so to start off, what is the edge coloring problem? So as input to this problem, we're given a simple undirected graph, G equals VE, and our objective is to compute a coloring of the edges in this graph such that no two edges sharing an endpoint receive the same color. So if the number of colors that our coloring uses is k, then it's easy to see that we need at least delta colors, where delta is the maximum degree of the graph. And this just follows from the fact that if you look at some maximum degree vertex in the graph, every single edge instant on this vertex will necessarily need to receive a different color, okay? So really the interesting thing here is how small can we make k, the number of colors that we use, okay? Because trivially, we could just assign a different color to every edge and we'd be done. So Vizing's theorem from the 60s shows that any graph can be colored with at most delta plus 1 colors, okay? And if you consider something like a triangle, for example, we can see that some graphs actually do require delta plus 1 colors. And in general, it's NP hard to determine if a graph is delta colorable in general. So delta plus 1 is really the best that we can hope for from an algorithmic perspective, okay? So a natural question arises, which is how fast can we compute such a coloring of a graph? So Vizing's original proof of Vizing's theorem is inherently algorithmic and immediately gives an MN time algorithm for this problem. This was subsequently improved upon by Arjamandi and Gabo et al. Independently, who showed how to achieve a running time of m root n up to some small polylog factors. And then this was not improved upon for a very long time until much more recently, Cinnamon showed how to shave off the small polylog factor from the running time of this algorithm, really by just having a slightly different analysis, okay? And then more recently, there was a sequence of works which improved upon the running time of m root n for this problem. So here there were two independent and concurrent works, one appearing at Fox and one appearing at Soda, which use completely different techniques, and which one of these is faster or slower actually depends on the density of the graph being considered. And then there was a subsequent work which combined both of these two ideas and techniques, and also developed some different tools and gave a further improvement and obtained a running time of mn to the 1/4. Okay, and it's also been known how to delta color bipartite graphs in near linear time deterministically for quite some time. There's the case of bipartite graphs is much simpler here, and there is an algorithm which very crucially exploits bipartiteness in order to achieve a near optimal algorithm for this problem already, okay? So as our main result, by taking a completely different approach to the problem to these recent works, we obtain the following result, which shows that we can compute a delta plus 1 edge coloring of a graph in near linear time with high probability. And in fact, we get a running time of m log delta, so we even match the running time for bipartite graphs, okay? So our algorithm also extends to multigraphs. So there is a generalization of Vizing's theorem, which shows that you can always compute a delta plus mu edge coloring of a graph, where mu is the maximum edge multiplicity. And it was shown by Shannon even earlier that you can always compute a 3 delta by 2 edge coloring of a graph. And our algorithm can obtain both of these bounds in m log delta time as well, okay? So we obtain a near linear running time, so near optimal running time for the problem of computing a delta plus 1 edge coloring of a graph, okay? So as a warm-up, I'm now going to discuss Vizing's original algorithm and the ideas used in order to achieve this MN running time, which we will be using in our algorithm as well. So Vizing's algorithm works as follows. You start off by creating an empty coloring of the graph, and then you scan over all of the edges in this graph in a completely arbitrary order. And while scanning the edge EI, you extend the coloring of the graph to this edge EI, okay, which is currently uncolored when you start this ith iteration. So suppose we have some edge UI VI, which is currently uncolored, and consider missing colors at the endpoints of this edge. So we say that the color alpha is missing at UI if there is no edge with the color alpha currently incident on the vertex UI. Okay, and whenever we color a vertex with some color, say red, this indicates that there are no red edges touching this vertex. Okay, so that red is missing at that vertex. Okay, so we can consider some missing colors at these endpoints, which necessarily exist because we know that we have delta +1 colors, and there are at most delta edges incident on every vertex, so there will be some color which is not assigned to any of these edges. Okay, and we can then consider the red-blue alternating path starting at the vertex VI in this edge. Okay, so we first consider whichever red edge is touching this vertex here, which is missing blue, and then the blue edge, which is touching the other endpoint of this edge, and so on until eventually this path becomes maximal and there are no other edges that we can add to this path. And note that there cannot be any blue edge touching this vertex because by assumption, this vertex is missing this color blue, okay? So we can then extend the coloring to this edge UI VI by first flipping the colors of this path, meaning that all of the red edges go to blue and all of the blue edges go to red. And after performing this operation, the color red will now be missing at the vertex VI. So this color red is now missing at both of these endpoints. So we can simply color this edge red, and we've successfully extended the coloring to this edge while maintaining the property that the edge coloring is proper, right? So that no two edges have like with the same endpoint have the same color. So what is the running time of this algorithm? Well, we perform m iterations, one for each edge, and each iteration can be implemented in time proportional to the length of the path that's being flipped with basic data structures, which is going to be at most big O of n with a very crude upper bound, because in the worst case, it will contain every vertex in the graph, okay? And thus we get a running time of big O mn with this very harsh analysis, which is saying that, in the worst case, every single one of these paths that we are flipping, covers the entire graph. So we get this very bad bound of mn. It's worth noting that if this path ends back at UI, this doesn't work because flipping this path will just switch the colors alpha and beta from being available at these two endpoints, but won't make the same one available at both. So then we would have to do something completely different in this case. But this can't happen in bipartite graphs because the union of this edge and this path makes an odd cycle. So what we've seen here is a proof of Vizing's theorem for bipartite graphs, and the general proof requires some additional slightly technical machinery, okay? So a useful insight that we can get out of this algorithm is that suppose we have multiple vertex disjoint uncolored edges whose endpoints are missing the same colors alpha and beta, okay? Then we can consider all of the alpha beta alternating paths starting at let's say the endpoints of these edges which are missing blue. And we can see that the total length of all of these paths will be big O of n. And that's just because if you look at the subgraph induced by the colors red and blue, it will have maximum degree 2. So it will just be a bunch of vertex disjoint paths and cycles. So all of the lengths of these paths will be big O of n. And this means that we can flip all of these paths in time big O of n, making red available at the endpoints of all of these edges. And then we can just color these edges in with red, okay? So the idea here is that we're creating, many uncolored edges of the same type, where the type here, we'll define it formally in a moment, but it just refers basically to this pair of colors alpha and beta. And if we have this situation where we have lots of edges which are missing the exact same colors in a bipartite graph, we can extend the coloring to all of them at the same in time big O of n, instead of just doing it to only one of them in time big O of n, okay? And once again, these bad cases where an edge starts at some blue, some vertex missing blue, and ends at some vertex missing red can't happen here just because of this assumption of bipartiteness, okay? So what is our objective here? Our goal is to extend a partial coloring that contains only a matching of uncolored edges. So extend the coloring to all of these edges in this matching in near linear time. And this might seem like it's a significantly easier task than computing a whole delta +1 edge coloring of a graph. But a very straightforward reduction by Gabo et al. Actually shows that if you have some delta +1 edge coloring, where all of the edges are colored apart from some edges that form a matching, If you can extend the coloring to these edges in near linear time, then by some simple divide and conquer approach, you can then get an algorithm that computes a delta plus 1 coloring from scratch in near linear time as well. So really the hardest part of edge coloring, in the static setting here, is just coloring the last few edges. And this really captures the complexity of the problem. So if we can perform this task, which is much easier to deal with from a technical perspective in near linear time, we can compute the entire coloring in near linear time as well. So for simplicity, we'll also assume the graph is bipartite for now, and that it's near regular, meaning that the number of edges is just n times delta, okay? So the algorithm that we'll describe now is the first near linear time algorithm for bipartite graphs that uses alternating paths. The previous algorithms for bipartite graphs very heavily exploit bipartiteness in a way that will not extend to general graphs. And because we're only dealing with bipartite graphs, the algorithm will only use delta colors. It will be a bit simpler as well, okay? And this will introduce all of the key subroutines and insights that our final algorithm for general graphs will use. And it is straightforward to remove this assumption of near regularity. This is just to simplify a couple of expressions that I'm going to show. Okay, so how does our algorithm for bipartite graphs work? So given some uncolored edge UV, we define the type of this edge as alpha beta, if and only if alpha is missing at one endpoint and beta is missing at the other, or vice versa, okay? So if you have an edge UV, U is missing alpha, B is missing beta, and then we can also observe that there will always be an alpha beta alternating path starting at both of the endpoints of this edge as well, okay? Even though this path, in theory, it could be empty, right? But this is a very nice case because then this means that one of these two colors is missing at both endpoints, and then you can immediately color this edge, right? So our algorithm has sort of two components. So the first component is what we call color type reduction, which picks some arbitrary type alpha beta and makes many uncolored edges of the same type, okay? So the uncolored edges here will be fixed. They're just a matching of uncolored edges, which we won't touch, but we'll modify the colors of the edges that are already colored in order to change the types of these edges. Okay, so this color type reduction component will modify the coloring so that many edges have the same type. And then the second component, which we call uniform type color extension, takes many uncolored edges that have the same type and extends the coloring to all of these edges efficiently. Okay, and the idea here is that taking these two components together, we're moving from a framework where we're performing single edge color extension, so coloring these edges one by one, and we are now sort of parallelizing things. We are extending the coloring to batches of edges at the same time. And the idea is that we have this, big O of n running time, which appears when we're flipping a single alternating path in Vizing's theorem. And this is very expensive to do all of this work for a single edge. And the idea is now we are pre-processing the coloring in some way to create a bunch of edges that have the same type. And then we're spending this big O of n running time to color many edges instead of only one edge, and significantly speeding up the algorithm by doing this. Okay, so how does this first component, which creates many edges of the same type, actually work? Okay, so this is really the main technical insight of this paper. So we take lambda uncolored edges forming a matching, and in roughly n time, we modify the coloring so that a lambda by delta chunk of these uncolored edges have the same type, alpha beta. And here alpha beta is some completely arbitrary type, okay? So we can modify the coloring so that a 1 over delta proportion of these edges have the same type. And this subroutine does not change the set of uncolored edges at all. So they remain vertex disjoint, i.e. forming a matching throughout the entire running time of this algorithm. So how can we actually do this? What is the algorithm that performs this task? So suppose that we don't have that many uncolored edges of this type yet, otherwise we're already done. So suppose that we have less than lambda by 100 delta uncolored edges of type alpha beta. What we then do is we sample some uncolored edge uniformly at random. And suppose that the type of this edge is gamma delta, so green, yellow in this case. If either of them is either red or blue, it only becomes easier for us. And if the colors gamma and delta are the same, then we can immediately color this edge. Okay, so let's assume that gamma and delta are distinct and also distinct from alpha and beta. All right. So we can then consider the red-green alternating path starting at U and the blue-yellow alternating path starting at V, okay? So by our assumption, these two alternating paths are edge disjoint from each other, okay? Because they use completely different colors. So we can then flip both of these edges simultaneously, meaning that we can flip them in either order, but they won't interfere with each other, right? And we can observe that after flipping these two alternating paths, the edge UV will now have type alpha beta. Okay, so we'll have alpha missing at U and beta missing at V. All right, and this is always going to be true. But what we can also show is that with some large probability, let's say probability 0.99, this also does not damage any of the other edges that have type alpha beta, meaning that it does not take some edge that had type alpha beta already and now make its type something else. And we can guarantee that this is true as long as we don't have too many uncolored edges of type alpha beta, and here too many is roughly lambda over delta. So we can make roughly a lambda over delta chunk of these have the same type alpha beta, but not more than this. Okay, so by this key lemma, when we apply this operation, with some very good probability, the number of edges of type alpha beta increases. And we can also show that the expected running time of this procedure, which stops once you've created a lambda over delta roughly many edges of the same type, has a running time of n times some small polylog. Okay. So the second component of our algorithm takes a collection of edges that all have the same type, and in n time extends the coloring to all of these. Okay, so this follows immediately from the previous useful insight, which basically says that we take all of these edges of type alpha beta and the alternating paths starting from them and flip all of these alternating paths in big O of n time, and then simply color all of these edges because they're now missing the same color at all of their endpoints. Okay. So putting everything together, our algorithm takes a collection of lambda uncolored edges, and in n time modifies the coloring so that a 1 over delta proportion of them have the same type, and then in n time colors all of these edges of the same type. So to summarize, in n time, we extend the coloring to a 1 over delta proportion of these edges. So by repeating this delta times log n many times, we extend the coloring to all of these edges in the matching, okay? And we can see that since each of these, every single time we do this, we're spending n time, which is very fast. I mean, this is sublinear in the size of the graph. And we do this delta times, the total running time is n times delta, which is m by our assumption of near regularity, okay? So this is our algorithm for bipartite graphs and how this works. So how can we extend this to general graphs? So how can we even extend a partial coloring in general graphs, right? So our previous argument fails for non-bipartite graphs. In particular, if we have this alternating path starting at U, which also ends back at V, then it's not possible for us to extend the coloring to this edge just by flipping this alternating path. We need to do something more clever. And this is non-trivial, even ignoring the running time, and also requires us to use delta plus 1 colors somewhere, all right? So Vizing showed how to do this, and he did this by introducing a machinery which is now referred to as Vizing fans and Vizing chains. So given some uncolored edge UV of type alpha beta, we can construct a Vizing fan at this edge UV. And a Vizing fan, it won't matter too much for the purposes of this talk, but basically it's this edge UV, and then a bunch of edges incident on U and a bunch of specific missing colors at the endpoints of this edge. Okay, and this thing is what we call a fan. And then we also have a Vizing chain corresponding to this fan, which is just an alternating path starting at this edge U and going through one of the edges within this Vizing fan. Okay. So Vizing showed that you can always extend the coloring to this edge UV by rotating colors around this fan and then flipping the colors of the Vizing chain. Okay. So we can observe that, having a look at this diagram here, the sequence of colors appearing in these edges is the same as the sequence of missing colors appearing at these vertices in the Vizing fan. And what this means is that we can shift or rotate this fan by shifting the colors of these edges down this fan. So we can move this color blue from this edge down to the edge UV, and this color green down to this edge, which is colored blue, and so on. And we can shift these colors so that this first edge on this alternating path is uncolored. And then we can flip the colors of this alternating path so that all of the red become yellow and all of the yellow become red. And this makes it so that the two endpoints of this uncolored edge are now missing the same color red. So we can just color this in red and we have successfully extended the coloring. And there are various cases depending on where exactly the Vizing chain ends and so on, but the details here aren't too important. The main point here really is that, this definition is pretty difficult to work with for our purposes. And the reason for this is that we don't have any control over the second color being used in this alternating path that is being flipped by the algorithm. So our algorithm before and its efficiency for bipartite graphs really crucially was using the fact that you could have all of these alternating paths that had the exact same colors and we could flip them all essentially simultaneously in big O of n time, right? And we could do this by having many edges of the same type, red and blue, and flipping all of their corresponding paths at the same time. But now, even if we have many uncolored edges of the same type, their corresponding alternating paths, which are now coming from these Vizing chains, are not necessarily going to have the same colors. So we don't get the ability to efficiently flip all of the Vizing chains corresponding to a bunch of edges of the same path. So this completely breaks down the ideas that we had before. So these definitions are very challenging to work with for this reason. So instead of dealing with Vizing chains and Vizing fans directly, we use another intermediate object instead. So for this purposes, we use the definition of a U-fan. So this was introduced by Gabo et al. For different purposes. And the idea here is that we have two uncolored edges sharing a common endpoint U, such that their other two endpoints are now missing the same color, which here is just going to be blue, for example, okay? And the idea now is that if we have this U-fan object, and we do just consider the red-blue alternating path starting at V, if it does happen to end back at U, we can still flip this path, and we still make progress because after flipping this path, we have that this edge UW is now missing the same color at both of its endpoints, and we can color this edge UW with this color blue, okay? So this is a little bit different to how edges behave in general graphs, in the sense that whenever you flip this path and extend the coloring to this U-fan, you're only coloring one of the edges instead of both, okay? But it does mean that we can control both of the colors within the alternating paths. And that means that we can basically plug these U-fans into a very similar framework to what we had before, and they can play essentially the same role as uncolored edges in bipartite graphs, but instead they're playing this role in general graphs, okay? So how does our algorithm work for general graphs? So the algorithm has two phases. In the first phase, we create a bunch of U-fans, and we do this by taking many uncolored edges, and somehow our algorithm will either extend the coloring to these edges efficiently, or it will shift them around and turn them into U-fans, satisfying this definition that we saw before. And the second phase of the algorithm colors these U-fans, right? So before we had our algorithm for bipartite graphs, which picked some arbitrary type, made many uncolored edges of this type, and then took these edges that had the same type and extended the coloring to them. Now, we have an algorithm that does almost the exact same thing, but instead of doing this for uncolored edges, it does it for U-fans. And instead of extending the coloring to all of them, it can only do it to a constant fraction of them by this property that when you flip these alternating paths in U-fans and extend the coloring, you're only coloring one edge and not both. And then the algorithm will repeatedly use both of these two phases in order to color the entire graph, okay? So after applying phase 2, it will be left with a bunch of uncolored edges again. It will then apply phase 1 to either color these edges or turn them into more U-fans, and then repeatedly apply these two phases, okay? And it turns out that we can actually implement phase 1 deterministically in linear time as well, with some, a new algorithm that we designed specifically to just take uncolored edges scattered all over the graph arbitrarily, and move them around and solve them together into U-fans so that we can then feed it into the second phase of our algorithm. Okay, so thanks a lot for watching. If you want to see more details about this algorithm, for example, how we create the U-fans and so on, then feel free to have a look at the extended version of this talk, which is available on the TCS Plus YouTube channel. Alternatively, I will be attending STOC in person, so feel free to find me in person and ask me any questions that you might have. Thanks a lot.